Welcome to Chapter 5. The topic of this chapter is data preprocessing. When we collect data, we usually find that our data cannot be used for analysis as it is. For instance, when we obtain data by questionnaire survey, we often find many misspelled answers and many unanswered questions. These are just a few examples. There are many issues to be addressed in order to make our data ready for analysis. It is our task in data preprocessing phase. This chapter focuses on the basic principles and techniques of data preprocessing. By the end of this chapter, you will be able to explain why data preprocessing is important, explain the basic policies and operations in data preprocessing, and explain how to clean, transform, and reduce data. Data preprocessing is located in the phase of data preparation and data exploration in the data science workflow. Not all tasks in these phases are data preprocessing. Some tasks of these phases are data preprocessing tasks that are needed to make raw data to be ready for analysis. Raw data is the collected data that is just delivered from the data source and is its initial state, that is before pre-processed. In many cases, raw data is not appropriate to be analyzed as it is because of many reasons. So, data preprocessing is required to go on to the following phases. Depending on the data collection method, data type, data source, and other various factors, data preprocessing requires a large volume of tasks. So, it is not unusual that we need to use the most time for data preprocessing in a data science project. Roughly speaking, data preprocessing can be classified into three categories of work: data cloning, data transformation, and data reduction. These works are iterative and there is no one best procedure. We often need to go back to preprocessing after starting the analysis and modeling. Since data preprocessing tasks are iterative and explorative, this categorization is not a definitive one, and thus the three categories are somewhat overlap. In many cases, the raw data contains many erroneous entries and noises. So, data cleaning is often required to make the dataset be ready for analysis by modifying, imputing, or deleting missing data and noises. Data transformation refers to works where we make the dataset easier or more appropriate for analysis by transforming a variable or generating a new variable by combining multiple variables. Proper data transformation enables us to analyze data efficiently, and it can also improve the performance of causal and prediction models. Data reduction is to simplify the dataset by deleting unnecessary variables and putting multiple variables together. By simplifying data, the dataset is easier for us to handle and we can reduce the computation cost. When we use a large volume of data, the computation cost is very high, and thus the development of a causal or prediction model becomes very time-consuming. So, sometimes we use various techniques to simplify the dataset. In the following section, I will explain each of these works in detail. As the first section, let me show a practical framework of data cleaning and how to clean data. A data frame is a basic structure of a dataset. A data frame organizes data as a two-dimensional table consisting of rows and columns. Typical examples include a spreadsheet and an Excel sheet. Not all dataset comes as a data frame, but if we format a dataset as a data frame, it becomes easier for us to handle and analyze the dataset. In a data frame, each row should represent each observation. So, for example, if the data frame stores employee data, each row should represent one specific employee. If the data is a product sales data, each row should represent each type of product. A row should not contain multiple observations. And in a data frame, each column should represent a feature, a variable. A column should not contain multiple variables. And each cell should represent each observation's features. Multiple observations and multiple features should not be included in a cell. This data frame is a customer data, so each row should represent a specific customer. The structure of this data is not appropriate as a data frame. For instance, this row contains multiple observations. Total is not a specific customer, but a sum of multiple customers. So, this row contains information on multiple observations. And this column contains multiple features. It contains each customer's purchase amount and the sum of the all customers' purchase amount. That is, the column contains two features. Summary information such as total, sum, average, and the like should not be included in the column of each observed value. A cell of a data frame should represent a specific feature of a specific observation. So, these cells are not appropriate because they contain information on multiple observations and multiple features. Roughly speaking, data cleaning consists of two major tasks: deleting unnecessary data and modifying errors and anomalies in data. Containing useless data makes the dataset unnecessarily large, resulting in high computation cost. And a dataset containing too many rows and columns are hard to handle. So, it is often desirable to delete data that has no useful information. A dataset sometimes contains a lot of erroneous entries, spelling inconsistencies, and missing data. Missing data refers to data with no available value. These errors and missing data sometimes obstruct data aggregation and data modeling. However, we should avoid deleting data as much as possible because, as a basic principle in data management, we should keep information as much as possible. So, instead of deleting data, we should devise ways to modify the errors and impute missing data with appropriate values. We often encounter outliers in a dataset. An outlier is a data point with an extremely high or extremely low values relative to the nearest and the rest of the data points. In some cases, we should delete outliers regarding it as erroneous entries. But in other cases, we should keep them as legitimate data. In a dataset, some rows should be deleted because they do not provide us with useful information. Further, they sometimes bring confusion. Let's see a simple example. We have a dataset collected from data scientists in a company that stores employee ID, job, age, tenure, and year of experience. This dataset contains some unnecessary rows. Can you find them? First, there are exactly two same rows. Focusing on employee ID, we have two A004, and these rows have the same values in all other columns. So, we can say they are identical. In usual cases, we should delete the duplicated rows, leaving only one row for each observation. Duplicated rows should be deleted because they do not provide additional information and result in incorrect finding if they are included in the analysis. We can find one more unnecessary row in this dataset. A row that contains many missing data do not provide us with sufficient information for analysis, so sometimes it should be deleted. In this dataset, the bottom is an example. Three of its columns display NaN. NaN is an abbreviation of not a number, meaning that it is missing data. So, the bottom row contains only employee ID and job. So, it provides no information for meaningful analysis of this data. Moreover, in some cases, we should delete very old observations. For instance, in customer data, a customer who purchased our products 20 years ago but do not have visited our store since then can be deleted because the person may be no longer our customer. Moreover, in many cases, our products, services, and channels have been changed significantly in the past 20 years. Now we have a clean dataset, deleting the duplicated row and a row with many missing data. Next, let's delete unnecessary columns. In some cases, employee ID is unnecessary. If you have this dataset for a record of any employee's personal information, employee ID is meaningful because it identifies which row is who. However, if you build a causal model that identifies the major causes of work motivation, employee ID is not useful because it is just an assigned number, not a meaningful numerical values. Moreover, the purpose of building a causal model or a prediction model is to develop a generalizable model. That is, a causal model should explain the causality not for a specific observation, but existing or future observations in general. Similarly, a prediction model should make accurate prediction not for a specific observation, but future observations in general. So, when we build a causal model or prediction model, we often delete personal identification data, such as employee ID, customer ID, name, and so on. Second, in some cases, columns consisting of a single value do not provide us with useful information. For example, this is a dataset of data scientists, so all of the persons including in this dataset are data scientists. So the column job contains only a single value, data scientist. So in descriptive analytics, it is not meaningful to use the column job for grouping data. Besides, when we create a causal or prediction model, this column is meaningless because we already know everyone in this dataset is a data scientist, and using this column as a cause or predictor is meaningless. Thirdly, columns with many missing values should be sometimes deleted because it provides us with little information. Besides, columns with many missing values are sometimes unreliable because they are missing due to the fact that obtaining accurate information about the data is very hard. In this case, the column experience contains many missing values, so it can be deleted. However, we should remember the basic principle. We should avoid deleting as much as possible so that we can keep the information as much as possible. So, if a column contains some or many missing values, first we need to impute them with proper values rather than immediately delete them. And finally, sometimes we should delete a column that has virtually the same information with other columns. For instance, we have a column of employees' age. In this case, if we have a column that records each employee's birth year, we have two columns that have virtually the same information. We do not always have to delete the birth year, but when we build a causal model or a prediction model, including such similar independent variables will result in extra computing costs and distortion of the findings. The latter problem will be covered in the following chapters in detail. Let's delete the column of year of experience, but keep employee ID and job. Let's look at the job column. You may find that In ID A005, the column job contains misspelling. And in ID A006, there's an extra space between data and scientist. Next, look at the column age, and you may find that the age of ID A006 is 288. I don't know what age we can live to, but 288 years old is an unrealistic age for a data scientist. Maybe it is a typo of 28. Maybe one extra 8 was mistakenly inputted. As for the job column, you might already find spelling inconsistency in this column. Specifically, they are all data scientists, but not written in a consistent way. In many cases, the first D of data and S of scientists are written in capital letters. But in ID A003, the S of scientist is written in a small letter. And in ID A007, all the characters are small letters. Next, let's look at the column named Annual Pay. We can see that in all the observations, the annual income is $100,000, but computers cannot recognize so because of the unit inconsistencies and spelling inconsistencies. Despite these errors and inconsistencies, we humans can understand what each entry means because we can complement missing information and fix slight errors based on our existing knowledge. However, these errors and inconsistencies are not understandable for a computer, so they can result in confusing and incorrect findings. So, we need to modify them in the early phase of data analytics. Let's consider another example. This dataset records the number of downloads of game applications. The dataset contains 2 genres, and each genre has 3 game products. Subtotal of each genre and total number are also recorded. It is very easy to read, isn't it? However, it is not a good format for data to be analyzed. This formatting style is good as a table for reporting, but as a dataset to be analyzed using Python or other programming language, this kind of formatting is problematic. First, as a dataset for analysis, each row should consist of data of an observation. In this example, an observation is a game product. So, each row should store each game's data. However, in this data, the first row records fiscal quarters. They are headings, not an observation. Besides, there are rows that record subtotals and total. These rows do not represent an observation, but an aggregation of multiple observations. So, why is it problematic? Suppose we compute the overall average number of downloads. When we use Python to do it, Python computes the average by a column. That is, Python adds up all the entries in the downloads column and divide the sum by the number of rows. Python cannot automatically skip the fiscal quarter and will return error because average cannot be computed for a word. Besides, Python cannot automatically filter out subtotal and total rows, so they will be double added and thus Python will return a wrong average value. So we should delete the first row and rename the downloads column as Q1 downloads and Q2 downloads, for example. And we should delete the subtotals and totals so that each row represents one observation. Another problem in this dataset is that it contains some blank cells. Python recognizes blank cells and missing data. So, for instance, Python cannot recognize world soccer and exciting hockey as a product of sport game. Instead, the genre of this data is unidentified, and thus Python cannot aggregate data by genres. So, we should fill in all rows in the genre column. Some problems cannot be identified unless we inspect multiple rows for each observation. First, there are cases where values recorded in two columns contradict logically. For instance, in this dataset, age and tenure are each employee's actual age and organizational tenure, respectively. So, for each observation, the value in tenure cannot be longer than that in age. By creating a new column that records differences between age and tenure, we can identify this kind of problem. Here, I created a new column named age, tenure, diff by subtracting tenure from age. The value cannot be negative, so if we find a negative value, either age or tenure is mistakenly recorded. So, the case of ID B002 is impossible. It may be that either age or tenure is wrongly recorded. Second, there are cases where values in multiple columns are not logically impossible, but are empirically, customary, or institutionally unlikely. That is, they are virtually impossible. For instance, the case of ID B006, job title is director, but age is 17. It is not impossible, but very unlikely, because this person is too young as a director. The tenure is 1, so this person's correct age may be 37, 47, or others. In questionnaire survey, we sometimes encounter insincere responses. For instance, some respondents may choose the first alternative, even without reading each question. Needless to say, such responses are not useful as evidence. So, we need to check if some respondents gave same answers for all questions. We can also check insincere responses by inspecting a logical contradiction. Observations with too many logical contradictions should be deleted from the dataset because respondents might not read and answer the questions sincerely. Not only to check but also to prevent this problem, we can use reverse-coded questions like the question 1 and question 2. While in the question 1, higher score corresponds to satisfaction. In the question 2, higher score means dissatisfaction. Thank you for watching. Please thumbs up and subscribe to my channel.